Okay, so today is the 3rd. We've been talking about functions, and we've got some more to say about functions. So the main idea that we're considering today is when can a function be undone? When can you invert it? So I could say the undo button. So the undo for add 3 is subtract 3. In the sense that if you had some number and you added 3 to it, then you could get back to the original by subtracting 3. All right. And similarly, for divide by 2 is multiply by 2. So if you had a number and you divided it by 2, you could get back to where you were by multiplying by 2. But there is no undo. There is no undo for multiplication by 0. Because, if it was going to be like this, the undo for multiply by 5 is divide by 5. And if there was going to be an undo for multiply by 0, it would have to be divide by 0, but you can't do that. All right. So then our question is how can you tell what functions can be undone? All right. So this is where we left last time with the remark that had a title something like the line tests. So first, a graph is the graph of a function if every vertical line intersects the plot at most once. All right. So to a lawyer or a mathematician, which are to some degree like the lawyers of science, to some degree, because we really parse the language pretty hard. Quantifiers mean something very specific. So notably, in this sentence, every vertical line intersects the plot at most once. So there's 2 quantifiers. One of them is every, and the other one is at most once. All right. So let's look at that. So we're going to make 3 examples here. So there's a graph. There's a graph. And here's a graph. All right. And the question is that, so we're looking at graphs there. Are any of them graphs of functions? So concerning this leftmost one, we want to consider vertical lines. So here's a vertical line. And how many times does this vertical line intersect the graph? This particular one. How many red points does it touch? None. So it doesn't hit any of them. All right. So this quantifier is saying at most once, which means that what's allowable is 0 or 1. That's what at most once means. So this vertical line satisfies this condition. It intersects at most once because it intersects 0 times. So does that mean that this is the graph of a function? No, because in the end we have this other quantifier. It says every. It doesn't say if you can find a line that intersects at most once. It doesn't say that. It doesn't say you get to pick your favorite vertical line. So here's another vertical line over here. For example, this one. So this one intersects 0 times. And then if I take it and I start moving it to the left just a little bit, then I can make it bump the red, just bump it right up next to it. So bump, so it bumps right at that 1 point. So drawing that, so there's a vertical line that intersects 1 time. So is this the graph of a function? No. And why not? What part of the definition? Yeah, it says every, right? So you can see that if I just move in just a little bit, there'll be a vertical line that that intersects more than once. For example, this one intersects twice. So the fact that this one intersects twice, we can say, therefore, this is not a function. All right. So the way that to understand this is we could do it with a vending machine analogy. So if we imagine the vending machine again, but let's go with the imagination that doesn't require money. You just walk up to it and press buttons. Then the buttons are points on the horizontal axis. Okay, so in some sense, what this picture is saying, it's saying that if I push that button, the buttons that's right there, then it vends one item. One item comes out. So it would give me that output right there. So if I press that button, I get that output. And then, notice that if I push that button right there, then 2 things are vended. 2 things are output. Well, such a vending machine is not a function. Okay, because to be a function, it has to be the case that you press a button and 1 thing comes out, not more than 1 thing. So here, you press a button, 1 thing comes out, so that's good. But you press that button and 2 things come out, that's bad. So not a function. And then this button right here, this is where it's kind of the vending machine analogy breaks down a little bit. That would be an example of a button that's just not on the machine. So we could walk up to a vending machine and you could say, hey, press button A3, and I push it. And out comes a Snickers. Okay, great. And then you say, oh, okay, well now push button G4, and then I push it. And then out comes, like a Twinkie and some peanuts or something like that. Well, it's not a function then. And then you could say, well, press the raccoon button. And then I look and say, well, there isn't such a button. It's not there. All right. How about this one? Does this one, is this a function? Does every vertical line intersect at most once? Yeah. Because over here you can see that this kind over here and lines further to the left, they'd intersect 0 times. Similarly, if I was way over here. But then if I'm anywhere in the middle, like here-ish, you can see that that's 1 intersection. And so do you observe that no matter where I put that vertical line, there's always 0 or 1? Okay. So always 0 or 1 intersection. Therefore, yes, it's a function. Yes, it's a function. All right. Same thing's true of this one, actually. But I always put one like this up to avoid, because this is maybe confusing the first time you look at it. So notice that this kind has 0 intersection. This kind right here will have 1. And what about this kind here in the middle? Well, these will have 0. Is that okay? Yeah. Because the rule is that it just has to be that every kind of line has 0 or 1 intersection. Every kind of vertical line has 0 or 1 intersection. So yes, this is a function. Now, to give a vending machine analogy of this, you could say, well, suppose that the vending machine has like 60 buttons on it, but they're all numbered, like instead of A4 and all that, maybe they're just numbered just with a number, like 1, 2, 3, 1, 2, and then 3, and then 4. But maybe the buttons are labeled like 1 through 30. And then for some reason they skip some numbers, and then we also have 70 through 100. I don't know why you would do a vending machine like that, but all right. So that's like what this is. It's like you can press these buttons; those buttons are there. You can press these buttons; those buttons are there. But for some reason there's a gap. I don't know why, but okay. 2. A function is invertible when the graph of the function satisfies every horizontal line intersects the plot at most once. So notably, these two sentences are the same, except I switched the word from vertical to horizontal. Otherwise, those two sentences are the same. As a result, these are called the line tests, and this one right here is called the vertical line test. And would anyone care to venture a guess what this one is called? The horizontal line test. Because that's, how mathematicians name things. Again, 3 examples. All right. And so, now for each one of these, I want to ask, does it pass the horizontal line test? So, yes?
I just want to clarify, Dr. McCary. Last lecture, you said at least once for the horizontal line.
I said at least once?
Yes.
Oh, that's definitely a mistake.
Okay, so it is at most once?
It's definitely at most once. Okay. Wow, I'm glad you caught that. It's definitely at most once. Wow. I'm glad you mentioned that. It is at most once. All right. So does this one pass the horizontal line test? No. So we can go through the same sort of exercise as before. I could draw this horizontal line and say, well, how many times does this one intersect? 0 times. And that's at most once. So why doesn't it pass? Yeah, because it doesn't say pick your favorite horizontal line. It says every. So if I take this one and I move it up, then I can move it up to where I've got 2 intersections. Like right there and right there. And then I could move it up even just any amount further, and then there'd be 3, and that'd be even, in some sense, even worse. So, but all that we need is 2. That's enough for us to say, nope, not invertible. So not an invertible function. Okay, how about this one? Yeah. Yeah, because again, there's going to be, it's just like this one, except now we're doing horizontal lines. So this kind of horizontal line, that's going to have 0 intersections. And that's acceptable. And this kind of horizontal line will have 1 intersection, and that's acceptable. And do you observe that no matter where we put that horizontal line, there's always 0 or 1? Okay, good. So always 0 or 1 intersection. And therefore, yes, it's an invertible function. Invertible function. Okay, how about the last one? Does it pass the horizontal line test? And the answer is no. It doesn't. Now, if you were looking at it and you were thinking yes, then in the first place, I set you up to mess you up here and now, where there's no points at stake. But if you look at this and think, well, it looks to me like it passes the horizontal line test. Well, here's a different question that I'll ask. Concerning this graph, that one right there, is it the case that every horizontal line intersects it at most once? That is the case. That's true. But that's not the question that I asked. I didn't ask, is it the case that every horizontal line intersects this at most once? I asked, does it pass the horizontal line test? So now I'm going to ask a question that will be kind of absurd, but I hope it illustrates the point. So this thing that I'm holding up here, is it a red apple? No. It's clearly red. But what? It's not an apple, right? Yeah. It's not an apple, so it's surely not a red apple, right? So understand that the horizontal line test is asking if a function is an invertible function. So does this pass the horizontal line test? No. Why not? Because it's not in the first place a function. It's not a function. Why is it not a function? Doesn't pass the vertical line test. So, if you when I ask this question again, if I say, is this a red apple? And you say no, and I say, well, it's clearly red. Then then you should respond with, well, yeah, I don't dispute that, but it's not in the first place an apple, so it's definitely not a red apple. Okay, so when I ask the question, does this graph does it pass the horizontal line test? And if I tell you yes, then you say no, and I say, well, it's clear that every horizontal line intersected at most once. Well, that's true, but what? It's not in the first place a function, so it's certainly not an invertible function. So can you see the distinction? All right, good. So if you have an idea of what the functions look like, you can have a good idea about whether or not they should have an inverse. So I can't remember if it was Monday or Wednesday, but at any rate, recently, we had a question that was like this. It was something like, determine if f of x is equal to 3x squared minus 4, and g of x is equal to x plus 4 over 3 square root. Determine if these two functions that I give you are composition inverses. And then the way that we did it before is that we did the following. We said, well, we'll do f composed with g evaluate at x, which is f of g of x, which is, you know, dot 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 dot. We did a bunch of computation, and this got down to just an x. So that means that in this order, they're inverses when it simplifies down to x. So we got there and we said, okay, that's good. But concerning composition inverses, what else must you do? You have to check it in the other order also, right? So not just f composed with g, but also the other way. G composed with f, evaluate at x, which is g of f of x, which is dot 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 dot. We did some work, and it came to pass that it actually didn't simplify down to x. Can you remember what it came to? It was absolute value of x. So the fact that it didn't simplify down to just regular x, you know, our conclusion is that therefore they're not inverses. So do you remember that exercise? Now I claim to you that you have another way, and another way to see that these couldn't possibly be composition inverses, and this way is, for my money, even better and even faster. So we can do it like this now. So now let's consider if you were to do a sketch. Some sketches of these functions. If you were to plot them, if you were to plot y is f of x, it would look like this. Because it's 3x squared minus 4, that means that this is a quadratic, which means its plot is a parabola. So if you were to sketch that function, it would look like this. You know, make a table of values and plot some points. It would end up looking like that. And if you were to plot g, make a table, plot some points, g would end up looking like this. Okay. So now, just you know, taking my word for it that the plots look like this, we can have a look at these two, and I can ask. So notice that they're both functions, obviously, because they pass the vertical line test. There's always a 0 or 1 intersection. Okay. But how about this one? Is this one invertible? It's not invertible. It's not invertible because it doesn't pass the horizontal line test. Not invertible because, you know, for example, that one. How about this one? Is it invertible? Does it pass the horizontal line test? It does. So now what we're looking at is, we're looking at two functions, we're looking at sketches of them, and now I can ask the same question. Could f and g be composition inverses? And the answer is no, because f doesn't even have an inverse. So they couldn't possibly be inverses of each other. F doesn't have one, so g's, because f doesn't even have an inverse, g's definitely not it. Okay. So, so you could say, you know, therefore, f and g are not composition inverses because f doesn't have an inverse. So in a math context, it's when mathematicians are, you know, being chatty about math and all of that. One of the, you know, we're interested in several sort of stereotypical kinds of things, and one of the things that we're interested in is whether or not something exists, because when you're describing something mathematically, it's very important to verify that such things exist, because if no such things exist, then you can say anything that you want about them and it's true. So, here's such an example. So, could these be composition inverses? Could G be the composition inverse of F? No, it couldn't be, because F doesn't even have one. A comical example of this kind of reasoning is something like the following. Did you know that UTD has won every national football championship we've ever participated in? We're undefeated at the national level. Is that a true statement? It's true. The reason why it's true is because if you say, no, that's not true, then I say, oh, well, in that case, I need you to produce the game. I need you to show me the game that we lost. Your inability to show me that game, the game that we lost, means that we have won every game and we are undefeated. Of course, it's just as true to say that we've lost every game. That's just as true. And it's also just as true to say that every one of those games has been purple. Because the set of all such games is empty. There are no such games. Okay, so the existence of things is important, because when you're saying something about something, when you're making statements about things that don't exist, they're automatically true. All right. So if this opens up an avenue, so if we know the shape of functions, what they look like visually, then we can tell a lot about them. So here's an example. Let's look at square root. Make a quick table of values. So as for inputs, remember that square root, you can only, you can't plug in negative values. So I'll say 0, 1, 2, 3, 4, 5. So some of those values you can do in your head, like square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. These other ones, you know, you can do with a calculator if you don't already have them memorized. But I have them memorized, so 1.41-ish, 1.73-ish, and 2.24-ish, something like that. So you can verify that with a calculator if you care to. So now let's plot that. All right, so 0, 0, 1, 1, 2, 1.4-ish, 3, 1.73-ish, 4, 2, and 5, 2.24-ish, something like that. So now, if we were to plot lots and lots of points, or just sort of connect the dots smoothly, you'd see something that looks like this. Something like that. So that's the plot of y is square root x. All right. So let's make some observations. Isn't it curious that that it's sort of like all crammed up there in the top right? There's nothing on the left side. What I mean is that none of these vertical lines. There's nothing over here. And you can sort of read it like this, like there's input 1, 2, 3, 4. So at input 4, the output is 2, because the square root of 4 is 2. Now, why is there nothing over here? Yeah, these would be input values that are negative, and that's not part of the definition of the square root. So there's no plot over here. Okay, well, that realization is we can write that down here. Saying it sort of conceptually, the set of all inputs that are allowed. We have a name for the set of all allowable inputs. That's the domain. For the square root, that's 0 to infinity. And you can see that from this graph, from this plot or any plot, by sort of sweeping this vertical line. Notice that there will only be intersections from 0 onward. But besides that, we're also interested in the set of all outputs, set of all possible outputs. So we haven't given a name to that yet. So we'll do that here. The set of all inputs is called the domain. The set of all outputs, its name is image. So you want to know, the question is, what outputs can you achieve? Well, the output axis is the vertical axis. So for example, that point right there is -3. So is there an intersection with -3? No. You can't get the square root to output a -3 or a -4 or anything down here for that matter. So the smallest output that you can achieve from the square root is right there. If you put 0 in, then 0 comes out. That's the smallest thing you can get to come out. And then you can get any output greater than that. So you can get any output. So what I'm saying is that you can go as high as you want, and you're always going to have an intersection. Now up here you can't see it, but that's just because the intersections would be way over here, and I can't draw over there. So what's the image then? 0 to infinity. Okay. Now, is this invertible? Which is to say, does it pass the horizontal line test? It does. And this is a nice visualization of a fact that we discussed at the very beginning of the semester. So at the very beginning of a college algebra semester, I always ask a question like, what's the square root of 16? And many folks will say plus or minus 4. and that's not right. Now, I do not dispute. I agree entirely that if you square 4, you get 16, and if you square -4, you get 16. No dispute. But the square root of 16 is 4. And you can see that from right here, because the output couldn't be positive or -4, because look, the square root doesn't have any plot down here. That would be like asking, to give a different example, the square root of 3 is about 1.73-ish. Not plus or minus 1.73. If you said plus or minus, that would mean that there should be a point here and another one there. But in that case, it wouldn't be a function. Okay, good. Let's have another one. So how about y is x cubed? Now we've considered y is x squared. And now we're going to consider x cubed. So x, y, -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay, so I'll deal with the ones that aren't negative first. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. And then they start getting bigger pretty quick. So 3 cubed is 27, 4 cubed is 64. Okay, how about -1 cubed? Be -1. So notice that it's not like the square. If we were squaring, the negative would be squashed, right? So like -1 squared would be +1. But the negative persists because, in the end, because 3 is odd. So similarly, it'll be the numbers will be just the same, except we'll have negatives. So -8, -27, -64, like so. All right. So plotting this. So usually I take these bold tick marks to be 1, but these numbers are too big for that, so I'm going to take them to be 2. So these little things that are usually half, I'm going to say that that's 1. So we'd have 0, 0, 1, 1, and then already we're getting big, so 2, 8. So 2, and then 2, 4, 6, 8 there. And then at 3, I'd already be at 27, but that's like all the way up here ish in the table. So it's going up real fast. Going to the left, -1, -1, and -2, -2, 4, 6, 8, right there. And then if we were to plot lots of points, like if we were to plot something between 1 and 2, like 1.5 or whatever, and connect the dots smoothly, then we'd see a picture that looks like this. And the idea that I'd like for you to have, sort of the mental model, is it's kind of like a parabola. If you just look at this one side, you might say, when he reveals the other side, it might be a parabola. But it's sort of like it was a parabola, and then we twisted the left arm down so that the right arm is still up, but the left arm is going down. Okay, so concerning this, what's its domain? All reals. Because all of these vertical lines have an intersection. So even way over here, so like at at that point there's an intersection, but it's just way down there. But we'd eventually get to it. What's the image? Which horizontal lines will intersect? All of them. And then, is it invertible? Yeah. So to be an invertible function, it's got to be a function. It definitely is. And then every horizontal line has to intersect at most once. So in fact, they intersect exactly once. So the answer is yes. All right. Good. So now we're going to write down some families of functions. The first one will be lines. Functions that have the form f of x is mx plus b. So I'll make 4 little axes here. So I'm going to deal with the first 3 and leave the last one for the end there. So this leftmost one, I'll say that this is the case when m is 0. This one, when m is less than 0. This one when m is 0, and this one when m is greater than 0. And I'm just leaving this 4th one here for a moment. So for this for this line, m is the slope. So what we're saying is that this one's going to be a line with negative slope, a line with 0 slope, and a line with positive slope. So negative slope, here's such a line. 0 slope, that would be a horizontal line, and then positive slope, something like this. And specifically, we want to consider the domain, the image, and whether or not they're invertible. So for all of these 3, the domain is the same. You know, you're asking, what x's can you plug in? Well, any x. Visually, it's asking which vertical lines intersect. Well, all of them. So the domain for all of them is all reals, negative infinity to infinity. For the image, you're asking, well, which horizontal lines intersect? So how about for this? For this one right here? Which horizontal lines intersect? All of them, because I can't. I only drew that much of the line, but it goes up infinitely far. So I can't raise this high enough to where I'm completely above the line. So this would be negative infinity to infinity, and so would this one, for the same reasons. What about this one? Well, notice that there's no intersection down here, and there's no intersection up there, but for that particular horizontal line, we are intersecting. So that means that the image is just that one value, b. All right, that's the image. And then now, which of these are invertible? So is this one invertible? Does it pass the horizontal line test? It does. Same with this one. What about this one? No, right? Because here, this is 0 intersections. That's good. Up here, 0 intersections. That's good. But how many times does this one intersect? Infinitely many times. So that's like the most not invertible you could possibly be. So to make a vending machine analogy, an invertible vending machine would be like a vending machine where someone walks up to it, and then we put a curtain to where you can't see what they're doing, and then they push a button, and then they come out and say, hey, I got a Twinkie, and you have to know exactly what button they pressed. Well, that means that every button has to give you something different. You only could have gotten a Twinkie from button 8. That would be like this kind. This This one that's not invertible, this would be like a vending machine where there's like 100 buttons, but every single one of those little things, those turny things, every one of them has a Snickers in it. So if they walk out and they say, hey, I got a Snickers, do you know what button they pressed? No, you have no idea what button they pressed. That's like this one. There's one kind of line that's not represented here that I didn't bother drawing, and that's, you know, besides lines that slope down, lines that slope up, and lines that are horizontal, there's also lines that are vertical. Now, I didn't bother drawing that one here. Why did I not bother until just now drawing a vertical line in this remark that is titled function families? It's not a function. You know, so these questions, these things don't even make sense to ask for it. All right. 2. Power functions. These are functions that take this shape. F of x is x to n, where n is an exponent. So now I'm going to draw 5 little axes. Okay, then underneath them I'm going to write y is x for all of them, and then I'm going to come back and add something. So specifically what I'm going to add is I'm going to add an exponent. So for this I'm going to say y is x to 1, and then y is x to 2, and y is x to 3, y is x to 4, and y is x to 5. So it's the green bit that's different. So now the first 3 we know. So this, you normally don't write exponent 1. You just leave it. So this is like y is x. But that's a line, right, with slope 1 and intercept 0. So this one just looks like this. We already know that one. This is a parabola. We know that one. This one we did a page or 2 ago, y is x cubed. It's like the parabola, but it's like someone took the left arm and twisted it down. And notice that for the square, that it doesn't have any output down here. There's no plot down here. In the end, because when you're squaring something, that squashes negative values. You can't get negative outputs. Whereas this one you can. So now this is x to 4. 4 is also even. So if you take, say, like -2 and raise it to exponent 4, the result will be positive, because you have 4 negatives. So this one is going to end up looking a lot like the parabola, except it'll be flatter near the origin and steeper away from it. So it's flattish near the origin and then quite steep after it. Interesting. What will x to 5 look like? It's going to be like that one, except it's going to be quite flat, so it'll be sort of as if someone took x to 4 and twisted the left arm down. So it'll be something like this. And now notice that the odd ones all have the same behavior. It's like the right arm is up and the left arm is down. And the even ones all have the same behavior. Both arms are up. All right. And then this last row will be the last thing that we do. Oh, and notice that it's the odd ones that are invertible. The even ones are not. So now we have the radicals. F of x is nth root of x. And so now I'm going to draw 4, and they're going to be lined up vertically with these. for each one of these, I'm going to do y is square root x. And then now I'm going to come back and add the radical number. So radical 2, 3, 4, 5. Are we running out of time? Yeah, 30 seconds. So we did square root a couple pages ago. It looks like this. Now cube root, remember it's an odd radical, so you can give negative inputs. It will look like this. So it's defined on both sides. How about fourth root? How will it look like? Yeah, it'll be like square root, but it'll be flatter near the origin, or steeper near the origin and flatter away. And then fifth root will be like cube root. And here's what I want you to see, is that the connection is, of course, the odd-even thing. But what cube root is, compared to cubing, is it's you take the cube and you twist it, like this. Twist, and you get this one. Or twist, and you have that one. Twist. Mm-hmm. All right, so that's all that we have. I hope you have a wonderful weekend. See you in 8 days.